Hi everyone and welcome back to my channel in Economist. So in the previous video we have talked about how to conduct hypothesis testing using the slope parameter which is beta. Now in this video I will be talking about the hypothesis testing using the intercept parameter which is alpha. We will solve numerical questions on that and we will also derive confidence interval of alpha. And in the second part, we will be covering what will be the confidence interval for the error variance, which is sigma square. And again, we will do the same thing. We will conduct hypothesis testing on that and we will solve numerical questions to demonstrate the idea. So let's start. Test for alpha. Now, if you have seen my previous videos of, parameter estimation and the features of when we have derived the features of this alpha and beta, we have said that alpha is the blue of alpha cap is the blue of alpha, right? So what we can say? We can say that expected value of alpha cap is alpha, and variance of alpha cap can be written as this: sigma square 1 upon n plus x bar square upon sxx. So if you haven't watched that video, please see the blue. When I have derived the blue properties of alpha and beta, there I have in details described how to obtain this particular thing, how to derive the expectation and how to derive the variance of this estimated alpha cap, right? So what we can say, combining these two things, we can say alpha cap, this follows a normal distribution. We have assumed it to be a normal distribution with mean alpha and the variance is this, right? Now, if you standardize, again the same thing, alpha cap minus alpha upon the standard error of alpha cap. This will follow a normal distribution. And we know RSS follows chi-square distribution. So if you combine these two things, exactly the same process as I have done for beta, you will see this. The test statistic, that we will use is like this: alpha cap minus alpha, standard error of alpha cap, and a cap of this as well. Why this is cap? Because sigma square, the original sigma square is unknown to us. So everything that we will do will be estimated. We will estimate this values using the sample data and nothing is known to us previously. And can you remember what will be the distribution of this test statistic? This test statistic will follow T distribution with n minus 2 degrees of freedom. Again, if you haven't watched my previous video, the last video that I posted, please see that video. There I have explained in details how this T distribution is coming and how to determine this degrees of freedom. So degrees of freedom of T distribution will be exactly equal to degrees of freedom of chi-square distribution, right? I have explained this in the previous one. So this is what we have, where sigma cap square is nothing but RSS by n minus 2. This is what we know. So we have derived the test statistic. This will be our test statistic. Now the next step is to formulate the confidence interval. Confidence interval of alpha. How to do that? We write like this: probability minus C alpha by 2 n minus 2 less than equals to alpha cap minus alpha upon standard error of alpha cap less than equals to T alpha by 2 n minus 2. What will be this probability? This probability will be 1 minus alpha, right? Now we can simplify this: probability minus T alpha by 2 n minus 2 into standard error of alpha cap, multiply this on both sides, less than equals to alpha cap minus alpha less than equals to T alpha by 2 n minus 2 standard error of alpha cap. This will be 1 minus alpha. Now what you can do? Probability minus alpha cap minus T alpha by 2 n minus 2 into standard error of alpha cap less than equals to minus alpha less than equals to minus alpha cap plus t alpha by 2 n minus 2 standard error of alpha cap, and this will be equals to 1 minus alpha. Now what you can do, you can multiply by minus 1. So if you multiply by minus 1, the sign will be changed. So probability alpha cap plus t alpha by 2 n minus 2 standard error of alpha cap. This is greater than equals to alpha, greater than equals to alpha cap t alpha by 2 n minus 2 standard error of alpha cap. So the final answer will be this, alpha cap minus t alpha by 2 n minus 2. Then you have standard error of alpha cap. Then it will be less than equals to alpha, and this is less than equals to alpha cap plus t alpha by 2 n minus 2 standard error of alpha cap, and it will be equals to 1 minus alpha. Right? So this is what you have. So how can you write the confidence interval in a compact form? The confidence interval of alpha is this, alpha by 2 n minus 2 standard error of alpha cap to alpha cap plus t alpha by 2 n minus 2 standard error of alpha cap. So this is the confidence interval, and the probability of lying in this, the probability that the population parameter lies in that confidence interval is 1 minus alpha, as we have already discussed. Right? So if we have this knowledge, we can define the decision rule. The decision rule is also the same. The decision rule that we have derived in case of beta will be applied here as well. So we consider three particular cases. This is the first case. This is the second case. And this is the third case. So basically these are three t distributions. They are symmetric about 0. I am drawing a freehand diagram, so it may not be accurate to scale, but just explaining the concept to you. So first case would be the case where it is one-tailed test, which basically means that H naught is, say, alpha equals to 0 versus H1. Suppose it is greater than 0. If this is the case, then the rejection region will come here in this particular place. It is a one-tailed test. This critical value will be T alpha n minus 2. So if your T computed value lies in this particular region, then you will say you will reject the null hypothesis because you are in the rejection region. This is the rejection region. Now there could be a second case of one-tailed test. One-tailed test, where what happens is that H naught is alpha equals to 0 versus H1 is alpha less than 0. Then this will be the rejection region, and the critical value is minus T alpha n minus 2. So if your T computed value falls in this particular region, you will say that you will reject H naught. And there is a third case, which is two-tailed test. Two-tailed test, which says H naught alpha equals to 0 versus H1 alpha not equals to 0. In this particular case, you will have two rejection regions. So this portion is rejection region and this portion is also rejection region. This value will be T alpha by 2 n minus 2, and this value will be minus T alpha by 2 n minus 2. So this is the decision tree. I hope this is absolutely clear to you. Now let us solve one question on this. So suppose your regression model is given as this, alpha plus beta x plus u. N is given to you as 10. Summation xi is given to you as 70. Summation yi is given to you as 80. Summation xi squared is given to you as 600. Summation yi squared is given to you as 734. So if you remember, this is the same data set we have used for testing beta as well. Summation xi yi is given to you as 480. Now the question says, test the hypothesis, test the hypothesis that x and y are proportionately dependent, proportionally dependent at 5% level of significance. LOS means the level of significance. So here the question is a little different from before. It says test the hypothesis that x and y are proportionately dependent at 5% level of significance. What does this mean as proportionately dependent? See, our model is this: y equals to alpha plus beta x plus u. Now, proportional relationship means that y and x has one-to-one relationship, proportional relationship. So, in order to have proportional relationship, what do you need? Suppose this is the estimated model. Y cap is alpha, beta cap x. This is the estimated model. Now, if you want a one-to-one relationship, then what do you need? You want to test alpha is zero or not. Right? Alpha is zero or not. So, if you consider alpha to be zero in our original model, then what will happen? Y cap will be beta cap x. Or let us not write y cap, let us write it y. So y will be beta cap x. This is what we have. So y upon x will be beta cap. So a proportional relationship exists between x and y only when alpha equals to 0, right? I have written this thing because the meaning of proportionally dependent has to be understood. So y and x are proportionally related means that there should be a constant of proportionality between them, which is this particular thing here. Beta is the constant of proportionality, right? So this is what we need to test. So we will test that alpha is 0 or not. If alpha is 0, we will say that yes, there exists a proportional relationship between x and y. If alpha is not equals to 0, that is, it is statistically significant, then we will say that no, there is no proportionally dependent relationship between x and y. Right? So let us do that. So what will be our null hypothesis? Null hypothesis will be alpha is equals to 0. We have to test this null hypothesis. We have to test this particular null hypothesis against the alternative hypothesis H1. H1 is alpha not equals to 0, right? So what will be the test statistic as we have derived already? What is the test statistic? To test H naught, we use the test statistic, which is T, nothing but alpha cap, standard error of alpha cap, because under H naught C, alpha is 0. So alpha cap minus alpha you need not write, because under H naught, we compute the test statistic under H naught. Under H naught, alpha is 0. So here you can mention this, but any which ways it is 0. So I haven't mentioned it before. So you may not write it. So under H naught, it will follow Tn minus 2, right? So you have to compute this particular thing. First compute alpha cap and then compute what will be the estimated value of standard error of alpha cap separately, and then if you divide this thing, you will get the computed value of T. So let us do that. Okay. So firstly, what is the total sum of square? Total sum of square is SYY. This is summation yi square minus n y bar square. This is the same thing we have computed previously. If you look from the data, we have got this to be 94. What is ESS? ESS we found out. ESS was 58.16. So what will be RSS? RSS is simply TSS minus ESS, which will be 35.84. If you have RSS, then you can simply compute sigma cap square, which is RSS by n minus 2. N is 10, so n minus 2 is 8. So 35.84 upon 8. This will come out to be 4.48. So you have got the value of sigma cap square. So what is standard error of alpha cap? Standard error of alpha cap is root over of sigma cap square 1 upon n plus x bar square upon sxx. Now you have all the values. Sigma cap square we have calculated to be this. N is 10. X bar is what? X bar will be 70 by 10, which is 7. And sxx, we can compute that. This will come out to be, sxx will come out to be 110. We have computed all these things while calculating beta, test for beta. So please go and watch that video before coming into this video. So what will be the standard error? It will come out to be 1.57 approximately. You can do it for yourself. You can compute this thing. I have already computed this. This will come out to be 1.57. Now find out what will be alpha cap. Alpha cap is y bar minus beta cap x bar. You have got all the values with you. This is 8 minus 7 and this will be minus 0.727. So alpha cap will come out to be 13.08. So this is basically alpha cap and this is the standard error of alpha cap. So what will be T computed? T computed value will be alpha cap upon the standard error of alpha cap, which is 1.57, which will come out to be 8.34 approximately. And what is T critical value? T critical value will be 0.0258. This value, if you look from the T table, it will be around 2.306. So what we see is that T computed is clearly strictly greater than T critical value. T computed is strictly greater than T critical value. So if you see from the diagram, if this is the case, then the critical value is like this, 2.306. Here you have minus 2.306, but your computed value is somewhere here, 8.34, right? So it clearly falls in the rejection region. So what we will say, we will conclude that we will reject H naught. So what will be the conclusion on the basis of the given sample, on the basis of the given sample, we can conclude that X and Y are not proportionally dependent at 5% level of significance, and we reject H naught. So this will be the entire explanation. So what I have done is that, so this was the question that we are solving. So these data are available to you. These data are available to you. This is a two variable simple linear regression model. You wanted to test the hypothesis that X and Y are proportionally related or not. If X and Y are proportionally related, then this value has to be statistically zero, statistically insignificant, at 5% level of significance, we should have that alpha is 0. But we conducted this hypothesis testing and we have clearly shown that there does not exist any proportionally dependent relationship between x and y at 5% level of significance, and we reject h not on the basis of our test. This is the test that T computed value, which is this. T computed values lie somewhere here, 8.34, but our critical value was 2.306. So it is clearly greater than that. The computed value exceeds the critical value, which gives us this confusion. So this is how you perform hypothesis testing using alpha. If this is one question, if I get other questions, I will post it in the community, or I'll take a separate class on that, right? As of now, this much was from my side. Now, let us move to the test of error variance. Error variance means sigma square, right? Error variance. Now, in order to do that, what we will do, we define the null hypothesis. Null hypothesis is sigma square is some hypothesized value, which is this. We will assume this is the test null hypothesis basically. Null hypothesis that sigma square is some specified value. Suppose it is 2, suppose it is 4. The sigma naught square is some specific value basically. Again, we want to test h1, sigma square is not equals to sigma naught. So this is our problem. This is what we want to test. Then what will be the test statistic? The test statistic that we will use is a little different from what we have used for alpha and beta. It will be chi-square. Chi-square. Then here what you have, n minus 2 sigma cap square upon sigma naught square. The sigma naught is basically the naught that we have used in our null hypothesis. Here. Test statistic, please remember, it is always computed on the assumption of null hypothesis is true. So we are substituting the null hypothesis value here. So chi-square, this is n minus k. It is k because n minus k is n minus 2 here, because we have two parameters. K is number of parameters estimated. So here we have only two parameters, alpha, beta. But if you are extending it for MLRM model, you have to substitute the particular value of k, right? So under h naught, which will follow chi-square distribution with n minus 2 degrees of freedom. So this thing and this thing will be same. If you have n minus k parameters, here it will be chi-square with n minus k degrees of. This will be the test statistic and the distribution of test statistic. Now what we will do, we will find out the confidence interval. Let's see how to find out the confidence interval. Probability chi-square 1 minus alpha by 2 less than equals to n minus 2 sigma cap square upon sigma naught square less than equals to chi-square alpha by 2 1 minus alpha. Why this is so? Because chi-square is a right skewed distribution which can only take positive values, right? It can only take positive values. So here you have 1 minus alpha by 2 and here you have only alpha by 2. I hope this is clear. Chi-square distribution is a positively skewed, right skewed distribution which can only take positive values. So probability 1 minus chi-square. Let me not write sigma naught square here. This will be sigma square. So greater equals to sigma square n minus 2 sigma cap square greater equals to 1 by chi-square alpha by 2. This is equals to 1 minus alpha. Then probability n minus 2 sigma cap square upon chi-square 1 minus alpha by 2. This is greater equals to sigma square, which is greater equals to n minus 2 sigma cap square chi-square alpha by 2, which is equals to 1 minus alpha. probability n minus 2 sigma cap square by chi square alpha by 2 less than equals to sigma square less than equals to n minus 2 sigma cap square chi square 1 minus alpha by 2, which is 1 minus alpha. So this particular thing will be the lower class interval, and this particular thing will be in the upper class of the confidence interval basically. And this is the confidence interval. This is the lower confidence interval, and this is the higher or upper confidence interval basically. And that is how you define the confidence interval for error variance. Diagrammatically, what we know, this is the case. Diagrammatically, a chi-square distribution will look like this. This is 0. What will be the shape? Shape will be like this, and then it will go like this. Higher values towards the, longer tail towards the higher values of x will give you a chi-square distribution. And the critical regions will be like this, here and here. This is one critical region. This is another critical region, and this is a chi-square distribution. Basically, this value is chi-square 1 minus alpha by 2, and here the value will be chi-square alpha by 2. Right? This is what you have, and this portion is the acceptance region, this entire portion in the middle. This entire portion will be the acceptance region. This will be the acceptance region, and this particular thing will be the rejection. This particular region and this particular region, they are the rejection regions. Rejection region. This is also rejection. I hope this is clear. So this is what is happening here. We have already derived the lower class interval and higher class interval of the confidence interval, right? Now, what we will do, we will solve a question, and by that we will end our session for today. Let us see the question. So the question says you have this alpha plus beta xi plus ui. This is the model that you have, and you have already run a OLS regression on this, right? You have run OLS regression on this model, and you have got the residual values. Once you run the regression, you have got the residual values. And let us write the residual values for n equals to 10. The sample size is n equals to 10. We have to estimate the following regression with 10 observations. These are the 10 observations. For each of the observation, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For each of these 10 observations, you know what is UI cap. UI cap is nothing but the residual. If you are following my lectures, you will know the difference between error and residual. Residual means the estimated portion of the error. So these errors are given to you. Let me write the values. For first observation, it is 2.1. Then you have minus 1.3, 0.8, then minus 0.5, then 1.2, then minus 1.1, 0.7, then you have minus 2.2, then you have 1.9, and then you have minus 0.6. So this is the question. Then what you have to do? You have to test the hypothesis. You want to test the hypothesis that test the hypothesis that error variance is equals to 2. So sigma naught square is 2 basically. This is what you need to test. So we can define our null hypothesis as this: sigma square equals to sigma naught square equals to 2, versus our alternative hypothesis will be sigma square is not equals to sigma naught square, which is 2, right? Now, since the residual is given to you, you can find out the residual sum of square, that is the RSS. What will be RSS? RSS will be simply summation UI cap square, I from 1 to 10. So let us find that out. 2.1 whole square Then you have minus 1.3 whole square, then 0.8 whole square, minus 0.5 whole square, 1.2 whole square, minus 1.1 whole square, 0.7 whole square, 2.2 whole square, 1.9 whole square, 0.6 whole square. So if you do that, do the sum, you will get 18.94. So RSS is 18.9, right? Now, what will be the estimated sample variance? Sigma cap square is RSS by n minus 2, 18.94, n is 10, 10 minus 2, which is 8. So this will come out to be 2.3675. So what will be the test statistic value? Test statistic computed value basically. Chi-square computed. Chi-square computed, this will be n minus 2 sigma cap square upon sigma naught square. So 8, 2.3675 upon 2. This will come out to be 9.47. So this is the computed value of our test statistic. And what is the critical value? The critical value at 5% level of significance. From chi-square table, you can find the lower critical value. The lower critical value is chi-square 0.0258. This will come out to be 2.18. And the upper critical value is chi-square 0.975. So one is alpha by 2, another one is 1 minus alpha by 2. So you will get this 0.975. This value will be 17.53. You can take this from the chi-square distribution. Chi-square table, which will also be in your statistics or econometrics books. Okay. So what we see here, this is the scenario. Here you have 2.18 and here you have 17.53. And what was the computed value? So these are the two rejection regions that we have. And what was the computed value? Computed value was 9.47. 9.47 clearly lies in the acceptance region, right? So what we will write clearly, 2.18 is less than 9.47 is less than 17.53. The test statistic falls inside the acceptance region. Inside the acceptance region. And that basically gives you the conclusion that we fail to reject. We fail to reject H naught at 5% level of significance, which basically means what? We accept this null hypothesis, right? Fail to reject means we accept, fail to reject means we accept this null hypothesis, which means that error variance is exactly equals to 2, which basically means that the error variance is exactly equals to 2 at 5% level of security, right? So this much from my side for today. I hope you find this session helpful. If you do, please like this video and give me a thumbs up. Do subscribe to this channel, A in Economist. That gives me immense motivation to continue making such useful videos for you. And in the next video, I'll be starting off with heteroscedasticity. So stay tuned for that. And thank you very much for watching this video. Thank you for your time.